Okay, so the next thing that we have here, basically there is a concept over here which is about the section formula, and the section formula is basically, we have talked about this before, and it's basically about the case where, for example, suppose you have a line segment, for example. Suppose you have a line segment PQ over here, and if there is a point over here, for example, let's say that you have a point over here on this line segment, let's say call it point R. If this point basically divides this line segment internally in the ratio, for example, m to n, then using the section formula, we found for example, suppose that the coordinates of this point P are x1, y1, and the coordinates of this point are x2, y2. And now the coordinates of the point P in terms of x1, y1, x2, y2, and this ratio m to n would basically then be basically R. The coordinates of this point would be m times x2 plus n times x1 over m plus n, and the y coordinate of the same point would be m times y2 plus n times y1 over m plus n. That is basically the coordinates of this point R in terms of the coordinates of these two endpoints and the ratio m and n. Now, in this case, we say that the point R, is dividing basically is dividing PQ internally in the ratio m to n. Okay, and we have talked about this before, and we have, well, of course not here in these videos that I have recently done on YouTube, but we have used it, but actually in the same videos we have used this formula in the section that was related to analytical geometry in 2D plane, of course, and we have used this formula to do different things. Now, there is another concept related to this concept, which is, suppose that, for example, you have a line segment, for example, AB. Suppose that you have this line segment AB, and there is a point, for example, C, which basically divides the line segment AB externally in the ratio, for example, in the ratio m to n, for example. So what that means is that the point C is, of course, outside of the line segment AB, but on the segment AB produced, but on the line segment AB produced, meaning that you have to, for example, now depending on, of course, you need to be careful about these notations. For example, in the case of, at least in this, when you're talking about this concept, when you say AB it would be different from the case if you said, for example, BA. That means that then the point C would be on the other side somewhere over here, for example. So if I produce the line segment AB and basically to reach, for example, point C over here outside of AB, then this distance over here would be, for example, now we will talk about this, basically we will talk about this properly, but then, for example, this segment would be, for example, M, and this segment would be N, and that's basically something like a definition. When we say basically that, when we say that the lines, the point C divides the line segment AB externally, for example, in the ratio M to N, some situation like this is meant. So now what we want to do now is basically we want to, first of all, take a look at this whole situation and see what this means, and derive some formula for this situation where a point basically divides a line segment externally, because we have already done the internal part. We have already talked about it and used it extensively. But externally, I mean, even I haven't done this, never before really. So we will go and basically derive a couple of formulas for this situation, and then we can go back to our own discussion, which was basically which was the section formula related to 3D geometry. Because, and the reason why I'm doing this again is that because in the section formula related to 3D geometry, there is a part that basically deals with basically the point dividing a line segment externally in the ratio M to N, and if you don't understand this concept, then you're not going to understand that concept either. So that's basically why we have to do this. So now let's get started on this. So first of all, there is this website over here. Let me show you a website which is pretty amazing in terms of the basically the resources that they have on this website. This website is run by some, I don't know, founder from India. And they have all the CRT Solutions, GEE materials, and so on and so forth. And they have some math topics. So for example, if you go over here, math curriculum by grades, and these are basically the exact same things that you would get on this website, basically ncert.nic.in. If you go over here, that's the website where you can download these books from the website of the National Council of Education, Research and Training. And if you go, for example, to class 10, this is 10, this is 11, and then, for example, subject mathematics, and then, for example, mathematics, and go, you will get the same book that we are dealing with right here. And we are right now doing chapter, I suppose, chapter 10. No, not chapter 10. We are doing chapter 12, which is basically this chapter over here, and Introduction to Three-Dimensional Geometry. So you can basically download this whole book. This is the book that I'm dealing with and that I'm doing right now. And this, as you can see, for example, this is the section formula that I am doing right now. So you can download the complete book from here. Now, sometimes these books need a little bit of explanation. And in that case, for example, there are all of these websites, for example, one of which would be basically QMath, for example, and for the students who normally live in India, they need, for example, help with mathematics. So there is all of these websites and resources like that help them with their problems in mathematics and in other subjects as well. And well, there is all of these resources over here that anybody can use, of course. If you want to learn mathematics, you can use all of these resources for free. So what that means is that, for example, you can go over here and, for example, math concepts are building blocks of mathematical thinking has curated a list of math topics that are essential for all the students across grades. These math topics are explained in detail in resources such as math worksheets, math tips and tricks, and math formulae are available for the students to access on the website as well as download. For example, if you're for example interested in numbers and place values, addition, subtraction, multiplication, and subtraction. I think they meant division by this. Let's see. For example, if you go over here, then you will see that basically for example, some material and some explanation about, for example, division and multiplication and so on and so forth. So you can, what I mean to say is that you can actually find great resources on this website. The articles are very well written, and as I Google searched, for example, external division, I wanted to know what the definition of external division was, and I found this article, for example, which is a pretty amazing article. I mean, it's well written, very, very, very precise, and very helpful. So then you can basically go to, I don't know, CRT Solutions, and these solutions 7, 8, 9, 10, these are, for example, the solutions of these books over here. These are NCRT books, and there is basically there is also GEE materials, and these are also GEE materials. I don't know what GEE is actually. It's some sort of examination in India, but whatever that is, they have the GEE advanced free material for 11th and 12th grade, which is all about, for example, parabolas, circles, and so on and so forth. There is the GEE Foundation free material for 9th class and 10th class, for example. You can access all of these articles if you need them. For example, for example, let's say you want to learn about combinations. Combinatorics, which is, let's see what that is. Oh, that's about combinations, permutations, and so on and so forth, I suppose. So these are permutation as arrangements, and you see there are basically all of these articles over here that you can use. So that is a pretty amazing website, really. Okay, so now let's get started with the concept of external division, and let's see what that is. So basically, the external division So let's say that you have this line segment over here. You have this line segment. Let me move this thing to the other side. Okay, so let's say that you have this line segment over here. For example, this line segment, let's say that this is A and B. So this is a line segment AB. Now what we want to do, we want to find out the point lying on the extended line AB. So we want to find a point lying on the, you need to pay attention to the words here, on the extended line AB, or line segment AB, outside of the segment AB, basically outside of the segment AB, such that AC to such that AC to CB is equal to 3:1. This is the ratio. Now what that means is that, suppose that this is the line segment AB, and if this is AB, for example, and you want to, let me see, for example, you want to do it in such a way that AC to BC is 3 times that, so what that means is that if I, for example, I have to go basically this much over here. So if I extend this line segment, I will get basically over here, for example, I will get basically this point over here, and AC, let's suppose that, for example, AC to CB is equal to basically 3:1, is equal to 3:1. The ratio of AC to CB or BC is equal to 3:1. And here basically we technically say that basically C externally divides AB in the ratio 3:1. So we say that C externally divides AB in the ratio 3:1. And what that means, actually, it's like a definition. What that means is that AC to BC, and C being basically a point outside of AB, is the ratio of these two lengths is basically 3:1. So and it seems that basically there is a difference between these two statements, meaning that when you say C divides AB externally in the ratio 3:1, and when we say C divides BA externally in the ratio 3:1, these are two completely different statements. You cannot take, at least in this context, you cannot take AB for BA or take BA for AB. Meaning that, for example, in this case over here, if C divides BA externally in the ratio 2 to 1, what that means is that basically, if you have your A and B over here, let's say that this is A and this is B, for example. This is A and this is B. When we say that C divides BA externally in the ratio 3 to 1, then the point C is going to be somewhere over here, for example. And then BC would be, BC to AC would be equal to 3 to 1. So that's basically what this means. And well, logically, when you say that C divides AB externally in the ratio 3 to 1, that means that you have your line over here AB. You have your line over here AB, and then on the other side of this, on the other side of this point B, you have your point C, and then you can say that AC to BC is equal to 3 to 1. That's basically what this means. Okay, so that is that. Now, what we want to do now is we want to geometrically locate the point C if it divides AB externally in the ratio 3 to 1. Meaning that if you have, let's say this is A and this is, for example, B, and this is, for example, C. If C divides AB externally in the ratio 3 to 1, for example, we want to locate point C, know the coordinates of the point C. And basically in order to do that, there is something in these NCERT books called the basic proportionality theorem. There is something called the basic proportionality theorem. And what that is, I don't really remember. I have read this theorem before, but I don't remember. I do understand it, but I don't remember the exact theorem right now. So let me look the theorem up. We will talk a little bit about the basic proportionality theorem, and then we will move on with this concept. Okay, so the basic proportionality theorem. So these things are all connected. If you go to one place, then you'll have to basically talk about a million things really. And well, of course, some things it's necessary to talk about some things. So, and the basic proportionality theorem is one of those things. It's an important and useful concept in mathematics, in basic mathematics. So you need to be familiar with that. So the theorem is basically as follows. It says that if a line is drawn parallel to one side of a triangle, parallel to one side of a triangle, to intersect the other two sides in distinct points. The other two sides are divided. The other two sides are divided in the same ratio. What that means is that suppose that you have a triangle. suppose that you have a triangle over here, something like this, for example. And your triangle is, for example, this triangle ABC. Now, if I draw a line segment parallel to the base BC, call it, for example, DE, you see that there is these 2 points of intersections of the line segment DE with the 2 other sides of the triangle. And this theorem says that basically if DE is parallel to BC, then for example AD to DB is equal to AE to EC. That's basically what this theorem basically states. Now, in case, of course, the proof of this, and before we move on with the proof of this, I need to tell you basically that the converse of this, and the converse is also true. Meaning that if a line segment basically is drawn basically, if a line segment, that means that if a line segment is drawn in such a way that it intersects two sides of a triangle, intersects two sides of a triangle in such a way that it intersects two sides of a triangle in the same ratios, or in the same ratio, then the line segment is parallel to the third side. And what that means is that if AD to DB is equal to AE to EC, then you can say that DE is parallel to BC. So now if I want to combine these two statements together, so this is if P then Q, this is statement I can write it as number 1, and for example number 2. Number 1 says if P then Q, and P and Q are these two statements. Number 2, what it says is basically if Q then P. So if you want to combine these two statements together, you can simply write it as P if and only if Q. Sorry, you have to use one of them. You cannot use both. Meaning that you can write P if and only if Q. Or you can write it as P if and only if Q. So when you say P if and only if Q, or basically using this notation or using this notation, what that means is that if P then Q, this is true, and if Q then P, that is also true, and both of them have to be true. simultaneously so that you can write P if and only if Q. So then of course I can basically, you can put these two together and write this as, you can put all of these two together and write this as if, basically you can write DE is parallel to BC. DE is parallel to BC if and only if basically AD to DB is equal to AE to EC. So that is basically this whole theorem this way. Now in order to, of course, the proof of these theorems are useful in many ways. Of course, we are not concerned about examinations or I don't know, marks or anything. But when you can prove something, it is, I mean, it's beneficial in many different ways, which I don't want to, which I don't have to explain to you. If you pay attention to how a proof works in your in your mind, in terms of the mathematics in your mind, then you will understand it yourself, that you need to basically understand the proof of all of these theorems that basically you learn over here or elsewhere, basically in mathematics. So for this proof we need a construction, and the construction is basically you can have a triangle like this and call it, for example, A, B, C, and draw a line segment, for example, parallel to the base, join BE and CD, join BE and CD, BE and CD. So you can join, basically, if you call it this point, for example, D and E. Now the first part that we want to prove is basically the first part over here, that if DE is parallel to BC, then the ratios are equal, meaning that I'm assuming that DE is parallel to BC. So now if I have to connect these 2 points as a part of the construction, so that I can prove things here. And then I want to basically do a perpendicular to this line over here, and I want to create a perpendicular to this line over here, and I call this, for example, I call this point N and I call this point M, and that's all that we need here. So now what that means is that what we have here is that the area of triangle ADE, so we have the area of the triangle ADE is half of the base times the height. Of course, the area of a triangle is 1/2 of the base times the height, and which means that basically you can write it as, you can take the base as AD, and then the height would be basically EN. So that would be 1/2 of AD, 1/2 of AD times EN. Now the area of triangle BDE, this triangle over here, BDE, the area of triangle BDE well, I used to I used to not like geometry much, but well, geometry is really this big part of mathematics, and without geometry, of course, you cannot do anything. It's a powerful part of mathematics, really. Okay, so now again, so I can write this as equation number 1, for example. I can write this as equation number 1, that basically the area of triangle BDE, the area of this triangle over here, is the same as basically 1/2 of the base times the height. And as you can see, you can write this as again 1/2 of the base, which is BD, times the height, which is basically the height of this triangle, is of course EN. And since this angle is an obtuse angle, then of course the perpendicular distance from this vertex to the base happens to be outside of the triangle. So the triangle is this one, and the height would be EN. So EN. So that would be equation number 2, for example. Then you can write the area of triangle ADE. ADE, this triangle over here. ADE, this triangle over here. The area of triangle ADE is equal to 1/2 of the base times the height, which is equal to 1/2 of the triangle ADE. So the base would be AE times DM. AE times DM. And the area of the triangle DEC, would again be 1/2 of the base times the height, You can call this equation number 3. So triangle DEC is basically this triangle over here. So that's equal to 1/2 of the base. I'm sorry, 1/2 of the base is basically EC times the height, which is DM. I can call this equation number 4. Now, if you divide these two equations, you will get the area of triangle ADE divided by the area of the triangle BDE, triangle BDE is equal to basically 1/2 times AD times EN by 1/2 times BD times EN, and these two can cancel out, is equal to AD by BD. I call this equation A, for example. And then if I divide 3 and 4, what I will get is the area of the triangle ADE by the area of the triangle DEC. Triangle DEC is equal to 1/2 times AE times DM over 1/2 times EC times dm. And then you can cancel these out and you will get AE to EC. Call this equation, for example, B. And now, as you can see here, basically triangle BDE, the triangle BDE and triangle DEC are on the same base. So triangle triangle BDE, this triangle over here, and triangle DEC, they are on the same base, meaning that I'm talking about this triangle over here. Triangle BDE would be this triangle over here, and this triangle over here, basically DEC, this triangle over here. So these two triangles are on the same base and they have the same height because these two lines are parallel. So you can say that, let me make a screenshot here. So let me open this a little bit, bring it over here so we can put that window somewhere over there. Okay, so you can see that. So then you can say that the triangle BDE, triangle BDE, and triangle CED, or DEC, basically, DEC are on the same base, and between the same parallel lines, So what that means is that if you have basically two parallel lines over here, and if you have, for example, one triangle, if you take this distance over here, and if you form a triangle over here, and then if you basically, let me extend this a little bit, and then suppose that I have this, suppose that I have another triangle over here, suppose that I have this another triangle over here, I make it basically a little bit different, for example, this triangle over here. So the line that you have over here is basically the base of the two triangles. This is the base of the two triangles, and this distance is the same for both the triangles. And you know that the area of any triangle, really, of any triangle, is equal to 1/2 times the base times the height. So now basically the base, if I call it B, and if I call this height, for example, H, now if I call this triangle over here, for example, if I call it, for example, A, B, C, and D, now in this situation, you can see that basically the area of the triangle ABC is the same as 1/2 times the base, which is b, times the height, which is h. And area of the triangle DBC is equal to 1/2 of the base times the height. So you can conclude that the area of these two triangles ABC and is equal to the area of this triangle DBC. And of course you can see that they look pretty different, but their areas are exactly the same because they have the exact same height and the exact same base. So technically we say that since these two triangles are on the same base and between the same parallel lines, then what that means is that you can say that therefore the area of triangle BDE is equal to the area of triangle DEC. Okay, and over here what we had was that the area of triangle, basically this is BDE. So over here we had from these two equations we have the area of triangle ADE and triangle BDE, triangle ADE and DEC. So what that means is that you see that the area of triangle BDE is equal to area of triangle DEC. BDE and DEC. Since these are the same and in the numerators we have the same area, so I can basically write this as, for example, I don't know, you can equate this, for example, to some value A, for example. Then this equation A becomes the area of triangle ADE divided by A, for example, is equal to AD to BD. And equation B becomes the area of triangle ADE to the area of triangle DEC, which is again equal to A, that is equal to AE to EC. Therefore, I can say AD to, and these are equal, of course. So AD to BD is equal to AE to EC. Which is what we wanted to prove. AD to BD is equal to AE to EC. So therefore I can say that in triangle basically ABC, if DE is parallel to BC, then you can conclude this thing, which is basically AD to BD is equal to AE to EC. Now the converse of this is also true, and I don't think we need to prove that anymore, but we will take a look at that as well. And that is also very interesting because because as you can see, there is something in mathematics. There is a technique of basically proving things, which is called proving by contradiction. There is something called proving by contradiction, and that technique has been used over here in order to prove that basically let me see. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. So what they do over here is that basically, as a given, is basically triangle ABC and the line DE intersect AB at D and AC at E. Triangle and a line DE intersecting AB at D and AC at E, such that AD to DB is equal to AE to EC. So this is basically the situation that we have. And we want to prove that, so basically we have drawn this line. I mean, to put it in simple terms, we have drawn this is a simple triangle ABC. We have drawn this line in such a way that these ratios are the same, meaning that AD to DB is equal to AE to EC. Okay? And we want to prove that if that is the case, then these two lines, DE and BC, are parallel. And then you need to do this, create this construction, and then this is basically called, proof by contradiction, meaning that what you do is a little bit actually is something in mathematics which is both interesting and beautiful, but also a little bit twisted. Meaning that what you do, for example, typically, what you do is that, for example, you want to prove that basically these lines are parallel. So if these lines are parallel, what you do now, I don't remember this proof exactly, but for whatever reason you need to prove that basically this point E can only be at this point on this side AC. Okay? You need to prove that, you need to show that this point E can only be at this point on this side AC. And that in this proof shows that basically then in some way that shows that basically this point, this line DE, is parallel to BC. Now, since you want to show that this point, this line will intersect basically this line AC only at point E, then you make an assumption that basically there can be another point of intersection of this line with this line AC, called, for example, E prime. And then through the process of proving, you prove that the points E and E prime are actually the exact same points, one and basically only one point, meaning that E and E prime cannot be two different points. They are the same points. And what that means is that then, for example, this line DE can intersect the line AC only at the point E, and that proves that, for example, this line is parallel to this line, and that's basically what you want to prove here. So that's basically the whole story here. But I do not really think that we need to spend any more time on this, because as I said, this proof is a little bit twisted, and well, it's not really required anymore. So let's get back to what we were doing, which was basically we were talking about the external, basically the external division of a line through a point, and so on and so forth. So I'm going to end this video here. I'm going to go back to that article, and then we will continue with the rest of the material that we had over there, which was basically when a point externally divides a line segment in some ratio. So I'll see you in the next video.